Yeah, yeah. Welcome everybody to this talk in the series of webinars on operator theory and operator algebras. So today we have Professor Apoorva Khare from Indian Institute of Science, Bangalore. Professor Khare has a large area of expertise on topics in analysis, algebra, combinatorics, and representation theory. And today he will be talking on total positivity history, basics, and modern connections. Okay, to you, Professor Khare.
Thank you for the warm introduction. So today I just want to give a very basic talk. There are no complicated tools or anything that I will use, but I wanted to give you a flavor of the area of total positivity, and there will be some operators in here as well, at least some operators. So let's begin. Let me remind you with some very standard notion. The real symmetric, all matrices in this talk will be real and symmetric. Such a matrix is positive definite if any of these equivalent conditions hold. So the first is how the name comes. The quadratic form is positive definite. This, if and only if all principal minors are positives, you take some set of rows, take the same set of columns, and the determinant is positive. If and only if all the eigenvalues are positive. Right? And these are, of course, ubiquitous in applications really as covariance and correlation matrices, but also in, say, the purer aspects of the less applied parts of mathematics, shall we say, analysis and so on. And of course, we teach it in calculus to every undergraduate. Correspondingly, today's talk is focused not on those matrices, but on totally positive matrices. Now the matrices need not be square. They can be rectangular. And it's just that every single minor should be positive. Not just the principal ones, but you choose 5 rows from any positions, 5 columns from any other positions, that 5 by 5 determinant should be positive. And similarly, if all the minors are totally non-negative, you call it a TN matrix. So for a TP, or totally positive matrix, all the entries are positive, all the 2 by 2 minors are positive, and so on and so forth. And that's why the matrix can be rectangular, because I don't care about I don't care about principal minors. And these matrices occur in a even more widely, let's say, in mathematics. So here are some of the areas and some of the people who have worked on them. So this all so morally, actually, total positivity in some sense started with, say, Laguerre in the 1880s. But let's say more directly, it started with the work of Schonberg, and then Fekete and Polya, and so on. So anyway, so it occurs in the analysis, of course, but also in probability and statistics, interpolation theory. Very recently in Gabor analysis, Groshnik, Romero, and Stockler have paper. Particle systems, this is very classical. Matrix theory, obviously, these are matrices, but also in representation theory, in cluster algebras, and many other areas. So, so that's just some of the names of some of the people who have worked on them. Okay, the title should tell you what I'm saying next. This is the folklore result that every real symmetric matrix is a positive semi-definite matrix if and only if all the eigenvalues are non-negative, and it is positive definite if and only if all the eigenvalues are positive. And clearly 2 implies 1, because take any principal submatrix, its eigenvalues are positive, their product is positive, and therefore the minor is positive, the principal minor. 1 implies 2 is the non-trivial part. Right? The same way, here is a result, which is basically saying the same thing, except I remove symmetric and just make it square, let's say. I remove principal and just make them all minors. So a real square matrix is totally positive, meaning all minors are positive, if and only if not just all the eigenvalues, but all the eigenvalues of all the square submatrices are positive. And similarly for totally non-negative. Okay? And I'm actually going to tell you the proof. The proof takes 1 slide, no more. So the proof uses Perron's theorem and Kroneker's theorem. Okay? So let's start with Kroneker's theorem. And so for that, I need to tell you what is a compound matrix. So if you have seen this, please disregard this part of the slide. If you haven't, let me quickly go through it. So the compound matrix basically says, take a set of rows, take R many rows and take R many columns, and look at the R by R determinant. So the set of all R by R minors of a matrix form the entries of the compound matrix. So if the matrix is n by n, then how many R tuples of rows and columns are there? Exactly these many, n choose R. So the compound matrix, the rth one, is a matrix of this size, indexed by rows, sets of rows and sets of columns, and the entry is the determinant. Okay? Let's lexicographically order the subsets. So by convention, the 0th compound matrix is taken to be the 1 by 1 matrix with the empty determinant 1. The first compound matrix has all the 1 by 1 minors, i.e. the entries. So it's A. The nth compound matrix is just the 1 by 1 matrix, which is the full determinant, and so on. And here are some basic properties you can verify. If A is lower or upper triangular, then so is the compound, every compound matrix. Intersect the two classes. If A is diagonal, then so is the compound matrix. If A is symmetric, and so on. The Cauchy-Binet formula actually is reformulated. It's not implying this. It is equivalent to this fact that the compound construction is multiplicative. Okay, because basically, yeah, you can check that as a fun exercise if you want. But as a corollary now, so the corollary is the following. If I want to look at the eigenvalues of a real matrix, let me write it in, or a complex matrix. Let me write it in Jordan canonical form. And then because of the Cauchy-Binet formula, if I write A equals M times J, the Jordan, times M inverse, then the compound matrix of A would be compound matrix of M times CR of J times CR of M inverse. But again, by the Cauchy-Binet, CR of M inverse is CR of M inverse, because everything is multiplicative. So what does that tell me? It tells me that the eigenvalues of this compound matrix are the eigenvalues of the matrix in the middle, but because J is triangular, so is the compound matrix. So it's literally the diagonal entries of the compound matrix of J. Nothing very profound here, right? Just all simple steps. And that is the flavor of this talk. I will tell you lots of simple steps and we will get to some results. Okay. So yeah, okay, great. So now this is what it is. But what are the compound matrix? What are the eigenvalues of a diagonal compound matrix of which is triangular? These are just the entries on the diagonal, but the entries on the diagonal are principal minors, which means they're R-fold products of the diagonal entries or eigenvalues of J. So that explains the last sentence here. Okay. So now, so given any matrix, therefore, any complex matrix, or in this case, real, the eigenvalues of this compound matrix are the products of eigenvalues of the matrix itself. So far, I've only told you about Kroneker's theorem or Kroneker's observations. Now comes Perron's theorem. So I have not yet worked with Perron. So let's number the, so now go back to the original setting. I have a totally positive matrix, which is a real square matrix, right? Number the complex eigenvalues according to modulus. Since this matrix is totally positive, every compound matrix has positive entries because that's the definition of totally positive. All minors are positive. And any matrix with a positive entries, with all positive entries, has a Perron eigenvalue. That's Perron's theorem, a precursor to the Perron-Frobenius theorem. Right? But what is, and also this eigenvalue is the largest in modulus. So it has to be lambda 1, lambda 2, lambda r, which means every one of these products is a positive real number. So lambda 1 is positive, lambda 1 times lambda 2 is positive, so lambda 2 is positive. Lambda 1, lambda 2, lambda 3 is positive, so now divide by lambda 1, lambda 2, so lambda 3 is positive, and so on. By the way, this proof is entirely, I believe, due to Gantmacher and Krein in 1937. So it's one of these amazingly clever proofs. It's compact proofs. Okay. And then, so first of all, you get that all of them are positive. Second of all, I claim that the eigenvalues are moreover simple. And that's because each Perron eigenvalue is simple. So lambda 1 is bigger than lambda 2. That's the first inequality. Lambda 1, lambda 2 is bigger than the other R-fold products of eigenvalues, which is lambda 1, lambda 3. So cancel positive lambda 1, you get lambda 2 is bigger than lambda 3, and so on and so forth. So that's how you prove the theorem that I told, that a matrix is, so the spectral property. Yeah. So if all the minors are positive, then all the eigenvalues of all the square submatrices are also positive. So that's how you prove this. Okay. So I told you some basic, the definition, some basic properties. Now let's go to examples. So this is a prototypical example of a totally non-negative matrix. It will show up later. This is the matrix which is square and lower triangular, and it has ones on the diagonal and below the diagonal. It has zeros above the diagonal. You can check explicitly that every minor is either 1 or 0, as far as I remember. This was worked out by Schonberg in his 1951 paper on Polya frequency functions. As far as I remember. Okay, generalized van der Waals matrices are totally positive. These are just these matrices that we have seen. Take positive increasing bases and real increasing exponents. And then this every such matrix is totally positive because you take any minor, it is of the same form as this. It is itself a generalized van der Waals matrix. So it's enough to prove the determinant is positive. And that is again something I believe that Gantmacher and Krein did at some point. Anyway, it's a very nice homotopy argument from the usual van der Waals to the generalized van der Waals. It's a very nice argument. Anyway, so this uses Descartes' rule of signs and nothing more. It's not too bad to prove. I won't prove it today. But yeah, as a consequence of this observation is a lemma of Polya, which says that the Gaussian kernel is totally positive. So I haven't told you what kernels being totally positive means. It's the same as matrices. Think of the kernel as a function on R cross R to R. Matrices are on finite set cross finite set to R. And the same idea. If you have the domain and the domain to be consisting of two totally ordered sets, well, take n rows and n columns. Look at the submatrix formed by those rows and columns. You get this entry in those submatrices, and that matrix must be totally positive. I'm going to prove this in 3 lines. So the point is, how do you prove such a result? You take any minor of this, right? So take 5 xj's and 5 yks. Well, that submatrix itself looks like the same form. So it's enough to again show that the determinant of such a matrix, of every such matrix, is positive. But this matrix itself factorizes in this very simple manner. You have a diagonal matrix of xj square on the left and of yk square on the right, and the cross term in the middle. This determinant is positive, this determinant is positive, and this itself is a generalized van der Waals matrix, and therefore we are done by observation 2 or example 2. Right? So it's just you build one on top of the other. That's all that, yeah. Okay, so these are examples of totally positive matrices, and then analogously you can define totally positive kernels, and this is one prototypical example of that. Okay, so now for a density theorem. I told you spectral properties, I told you examples, and now a density theorem. So recall, again, by sort of analogy with positive semi-definite matrices, every one of those can be approximated by perturbing by the identity, right? So you just add a small multiple, you get positive eigenvalues. So yeah, in other words, the positive definite matrices are dense in the PSD matrices, semi-definite matrices. The same thing holds for totally positive inside totally non-negative. And this is by Schonberg's student, Anne Whitney. And so she proved that the set of all m by n, so take any, fix any size, m and n, fix an order of total positivity. And what do I mean by that? I mean all the 1 by 1 entries are positive, all the 2 by 2 entries are positive, until all the R cross R entries are, all the R cross R minors are positive, sorry, not entries. Yeah. But maybe the R plus 1 by R plus 1 minor can be negative. One of them could be negative, for instance. Anyway, so the set of all m by n TPR matrices is dense in the set of all m by n TNR matrices. You can perturb. And that actually builds on the lemma of Polya that I told you on the last slide. So it uses this observation, it uses this, this observation of Polya to make things work. Anyway, it goes through verbatim if you use symmetric matrices, again with the same lemma of Polya's. And it also goes through for not just matrices, but for kernels. So there are some examples of kernels where totally positive is dense in totally non-negative. Okay. And I will tell you one example on the next slide to this. So first of all, let's define these kernels. So all you need to do is, you don't need to have kernels on 1 through n cross 1 through m, or R cross R to the real 9. You just need totally ordered sets in the domain. So given 2 such sets and a kernel from x cross y to R, you say that it's totally positive of order R if for any size less equals R, P, all the P by P minors are positive. So meaning you take P many X's, which are in increasing, arrange them in increasing order, take P many Y's, arrange those in increasing order, and then you look at the determinant. That should be positive. Okay. So that's the definition. We say that it's totally positive if it's TPR for every single R, for every single order of total positivity. Similarly, totally non-negative. Examples, if the domains are finite, then you get matrices, which we just talked about. If you have, let's say the domains are both R, so they're totally ordered sets. This is the van der Waals kernel really, right? So it's totally positive. And why? Because if you take any finitely many xj's and finitely many yks, then that was exactly what was in Polya's lemma. Right? It's just a generalized van der Waals matrix. Similarly, now if I take x equals y equals R and look at a slightly fancier version, which is I build on top of the previous example, k plus minus of x and y is this exponential. So the k minus was the Gaussian and k plus is e raised to plus x plus y squared. The claim again is that that is totally positive, and the proof is exactly the same as last slide. The key is that the cross term in the middle has a strictly positive sign, not a negative sign. So either minus and minus, like in the Gaussian, or plus and plus. So the same proof that works. So, but you see now, so here the functions k plus and k minus depend on x and y only through x plus y and x minus y. So these are really sort of Hankel function for x plus y and Toeplitz functions for x minus y. And so I'm going to talk about structured kernels. I will spend exactly one slide on Hankel kernels, and the rest of the talk will be on Toeplitz kernels. Okay, so let's start with Hankel kernel. So the kernel k plus is an example of a continuous Hankel kernel, meaning there is such a function of x plus y alone, which equals the kernel. So, okay, yeah. It turns out that such kernels were actually completely classified by Widder in the 30s. So suppose, so as I said, this is a talk full of very classical results, very, in some sense, basic, simple observations. And the idea is I will give you all the simple observations that lead you to one half of the proof, and all the subtlety and the complication lies in the other half of the proof, which I will not talk about. So this is one. So every continuous Hankel kernel is of this form. So clearly, such a kernel is of that form, in some sense, from verifying from the previous example, some kind of a similar proof. The converse, that there are no others, is the difficult part. And that will be the flavor of every other result in this talk that I tell you about, every other kind of if and only if result. So if X is an open interval, then every continuous Hankel kernel is of this form, where you integrate against a non-negative measure, basically. Moreover, the kernel is totally positive if and only if this measure has infinite support. Okay. So as I mentioned in the density slide 2 slides ago, there was density, Whitney density for matrices, but it was also true for some classes of kernels. This is one class of kernels. And this is because we understand the totally positive kernels among them. So here the Whitney density also holds in the sense that take any such kernel, then k of xy is indeed the limit of k epsilon, where you just perturbed by a small perturbation against the measure, against the Lebesgue measure, let's say. So that has infinite support. As epsilon goes to 0, you're good. Okay. So these are every k epsilon for epsilon positive is totally positive kernel, Hankel kernel, and k itself is the limit and it's totally non-negative. Okay, so that, as I said, is the first and last time we will see Hankel kernels in this talk. For the rest of the talk, I focus on Toeplitz kernels. So as we just observed earlier, the Gaussian is Toeplitz, and it is a totally positive kernel. So more generally, let me define. So Toeplitz kernel means there is a function, right? F from or lambda from R to R, such that k minus of xy is lambda of x minus y. In this case, lambda is just this function. So more generally, I can define any totally non-negative function to be lambda such that the Toeplitz kernel is totally non-negative. Take finitely many x's, finitely many y's, take the determinant, that's non-negative. So the first example is one we already saw. The second example is a degenerate one, a sort of Dirac delta example. Take a point and just take the kernel to be a constant, a non-negative constant on that point, 0 everywhere else. Why is this totally non-negative? Because you draw any submatrix xj's and yk's. So either you get C on the diagonal, or you have a 0 row or a 0 column. So the determinant is either C power something or 0. That's not too hard to show. So that's a degenerate totally non-negative function. Here is a monotone totally non-negative function and the exponential. It is not clearly this function on R to R is not integrable. Why is this totally non-negative? Again, you take xj's, you take yk's. The matrix you form is exactly this one. You can check, right? And this matrix is rank 1. So all the 1 by 1 entries are positive, and every 2 by 2 minor or larger vanishes because the matrix is rank 1. So this is totally non-negative. Okay. And now, so these are either vanishing nowhere, vanishing almost everywhere, or vanishing again nowhere. Here is a function that vanishes on a semi-axis. I take the function 1 above the origin and 0 elsewhere. And this can be verified to be totally non-negative by explicit calculations. But remember, I told you the first example of a TN matrix I told you was 1s above or below the diagonal, 0s above it. Well, guess what? That is a matrix that's drawn from a sort of a principal submatrix of this totally non-negative function or kernel, the Toeplitz kernel. So yes, because that thing happened, therefore you sort of verify this one. Then either you have a 0 row or a 0 column, or you get a principal submatrix of this kind, and then then life is good. You know how to do that. Notice that the last 2 examples are not integrable. The second example is degenerate. So now we are going to focus again in the rest of the talk, again one more slide later, On totally non-negative functions, which are on the one hand integrable, so they rule out these two examples. On the other hand, they don't vanish at least 2 points. So they are not non-degenerate. That rules out this example. It turns out the moment you are totally non-negative and don't vanish on 2 points, you don't vanish on the entire interval between them. Okay, so that's why to say it doesn't vanish at 2 points is the same as it doesn't vanish on an interval. It's really non-degenerate. And these functions are called Polya functions, Polya frequency functions. So traditionally in Schonberg's time in the 1950s, frequency meant density, probability density functions. It integrates to 1. Now we just sort of loosely relax it and say that we allow for rescaling. So it's integrable, but doesn't need to integrate to 1. Okay. So first of all, a function lambda from R to R is a Polya frequency function if it's integrable. Secondly, it's non-zero at least 2 points. And as I said, you can prove from that it's non-zero between them. So thirdly, the associated Toplitz's kernel is totally non-negative. Okay. And from that, because it's totally non-negative, all the 1-by-1 minors are non-negative. So this function is not only integrable, it is non-negative and integrable. That's by the definition itself. Okay. So these functions have a beautiful structure theory. Schonberg's first paper, where he introduced these in 1951. Well, technically it was his second paper as in published order, but first paper in the written, as it was written. And that followed 2 announcements in PNAS in 1947 and 48. But anyway, that first paper lays out a beautiful theory in crystal clear terms. It's really pretty to read, and it contains amazing results. And then, later on, Schonberg and 2 students of Polya, Eisen and Edray, and Schonberg student Whitney, they developed some more, and so on and so forth. And they connect to lots of different areas, also to splines, which I didn't mention. Examples. So as I said, the Gaussian kernel, of course, is integrable, is totally non-negative from the previous slide, and it's clearly non-zero everywhere. This function, the function that I told you on the last slide, the Heaviside function, if you will, this is not integrable. But if you multiply by e power minus x, then this is literally the density function of the exponential random variable. So this is indeed integrable. It's non-zero at 2 points. And I claim it's a Polya frequency function. So I claim that the Toplitz's kernel is Tn. Why? This is Tn because basically it's a more general fact. If you know that the function without this exponential is Tn, which I claimed last slide, so then you can claim that any exponential multiplication preserves total non-negativity. And that's because of the same proof as the Gaussian from the generalized van der Waals. That's the same proof as Polya's lemma earlier. You take xj's and yk's, you have to multiply this function by e to the xj minus yk times a plus b. And that means there's a diagonal on the left and a diagonal on the right. Take determinants and there is no problem. So it's the same exact proof as Polya's lemma. Okay? So again, it's a very short proof, and this is why this function is indeed totally non-negative as well, therefore a Polya frequency function. Okay, so that's another example. These are somehow the prototypical examples. Of course, you can also take the function which reflects this function around the x-axis. So you can take e raised to plus x times the characteristic function of minus infinity to 0. And that's a Polya frequency function. And so I've told you sort of three basic Polya frequency functions. And I can't tell you more examples because in some sense there are no others. And that's where I'm getting to in the second half of this talk. That some of these are the atoms out of which all Polya frequency functions are built up. And so to tell you how to build those up is the purpose of the next few slides. Okay, sorry, not the next few. The next few slides after these few slides. Okay, so before I tell you these properties, why the functions I told you were the building blocks, were the atoms, let me now get to Polya frequency functions and totally non-negative matrices when you think of them as operators. So given that this is a WOTOA talk, here are 2-3 slides on operators. Right? So first of all, let me start with matrices. So totally non-negative matrices, and similarly, as I said, Polya frequency functions have something called the variation diminishing property. And this is, okay, I'll tell you about that in the 2 slides, but let me tell you the property itself. So Schonberg proved the same property for matrices in 1930 in Matt Zeitschrift, and for Polya frequency functions in this, as I said, landmark paper of his in 1951. So the matrix property says, take any matrix and think of it as an operator. So it acts on Rm and takes them to Rn. Then if you look at the number of, so take any input vector, take 1, minus 1, 1, minus 1, 3, 4, 0. Remove the 0 entries. Look at the number of sign changes in consecutive entries. That's what I call S minus of x. Remove the 0 entries. Look at the sign changes. In Descartes' time and as late as Laguerre's time in the 1880s, variation meant sign changes. So that's why variation diminishing property just says the number of sign changes of the output vector A times X in Rn is less equals the number of sign changes in the input vector in Rm, a different number of entries. That happens when the matrix is totally non-negative. That is the variation diminishing property. For matrices, for kernels, now you think of a Polya frequency function as a kernel against which to integrate, and the variation denotes the number of sign changes again in the values of the function over the interval of integration. Now here is the property that Schonberg proved. If f is integrable on all finite intervals and lambda is any Polya frequency function, then the start with f, the number of sign changes in the input beats that in the output, where the output is just literally this convolution. It's the kernel against which we integrate. Now, clearly, of course, here, if the number of sign changes in f itself is infinite, if the input function was infinitely varying, then there is nothing to prove. This is less than infinity. I mean, what's the big deal? It's really when the number of sign changes here is finite that this kind of a smoothing operator or convolution operator has finitely many sign changes. In fact, at most that many sign changes. That's the non-trivial result that Schonberg proved. So that is the continuous version of the variation diminishing property. And this has a discrete variant as well, but not just for matrices, but for bi-infinite sequences. These are called Polya frequency sequences, and that's what I will discuss next. These are just sequences such that for any choices of input integers and on x and out input integers on y, you take the submatrix A of Lj minus Yk that has positive or non-negative determinant. So non-negative for Polya frequency sequences. In other words, you look at this infinite bi-infinite Toplitz's matrix. A0 on the diagonal when x equals y, A1 on the diagonal, a sub-diagonal where x is bigger than y, A minus 1 when x is less than y, and so on. Take finitely many rows and finitely many columns, the determinant is non-negative. That is a Polya frequency sequence. It's literally, again, a totally non-negative function or kernel on Z cross Z or Z cross Z. So now let me just tell you one slide about the history of total variation, total positivity or the variation diminishing property. Apparently I have two slides because this says part 1. So this name was coined by Polya in German, where variation, as I said, denoted the number of sign changes. So this was in use since Descartes' rule of signs, the word variation. And I keep mentioning Laguerre in 1883. Well, this is the result that Laguerre stated in his paper, I believe in JMPA. Suppose f is a real polynomial. Given gamma bigger equals 0, I look at the formal power series. Well, it's convergent, of course, but I look at the formal power series, e power gamma x times f of x. As a function of gamma, I can compute the number of variations. Right? So there are Taylor coefficients, Maclaurin coefficients, I look at them. And the point is, as if gamma equals 0, then this is just f of x. So there are only finitely many non-zero Maclaurin coefficients, which are the coefficients in f. So the number of sign changes in that for gamma equals 0 is finite because I discard all the 0 terms, remember. The claim is that Laguerre claimed was the number of variations even for any positive gamma is non-increasing in gamma. So it is bounded above, therefore, by the number of sign changes in f itself. And it is also bounded below always by the number of positive roots of f. So the fact that gamma equals 0 bounds this number of positive roots is called Descartes' rule of signs. This is a result from 1637 by Descartes, right? The fact that Laguerre claimed was that there are uncountably many values of this positive integer between those two integers. So this is really, really a huge refinement of Descartes' rule of signs. Now, it turns out that Laguerre apparently did not actually prove this fully. And that's what Fekete claimed, that he claimed in his letter to Polya, which was published in 1912, that Laguerre did not fully prove this. But I can do so, Fekete claimed, as a corollary of the following result, that P of t, which is be a formal power series with all the ck being non-negative. Therefore, with respect to the monomial basis 1, x squared, x cubed as an infinite vector, the operator of multiplication by p is exactly this, right? The constant term gets multiplied by c naught. The linear term changes to c1 times x naught plus c0 times x to the 1, then c2 x naught plus c1 x plus c0 x squared, that kind of thing, right? So this is just the convolution operator when looked at as a matrix. Fekete claimed and proved that if this matrix is totally non-negative as a one-sided matrix, In other words, this Polya frequency sequence C0, C1, C2 is a Polya, 0, 0, 0, 0, 0, C0, C1, C2 is a Polya frequency sequence. Then this gives you the variation diminishing property. So remember, Schonberg proved this thing for matrices in 1930, but actually Fekete had proved this for infinite, one-sided infinite matrices in 1912. And Laguerre had claimed this in some sense for a special case of e power x, e power gamma x in 1883. So really one can trace back the history of variation diminishing property and total non-negativity to sort of Laguerre in 1883, which made use of Descartes' truth of signs in 1637. Anyway, so, but I digress. So really what one has to prove, what Fekete proved was that e to the gamma x, if you look at the Taylor coefficients, which are gamma to the k over k factorial for ck, then that matrix is totally positive. That infinite matrix is totally positive, totally non-negative. And that actually can be proved with not too bad properties using just the Cauchy-Binet formula and some simple observations, but I will not do so today. But in the flavor of Polya's lemma, or the other simple proofs that I gave you, Kroneker's theorem, Perron's theorem, and so on, this itself for the exponential is not too hard to prove. Okay? I should point out that all these proofs that I mentioned and the one that I just told you right now, I actually managed to write about a 50, 60 page document, which is in my lecture notes on my website. These are part 4 of my lecture notes, where I introduce total non-negativity and develop all of these things in sort of from first principles. You really don't need to read anything or know sort of anything to read that result, except maybe one course in linear algebra and one course in calculus, like one variable calculus, like we teach undergraduates. But all of these things are such like beautiful and clever observations by Fekete and Schonberg and Guntmacher and Krein, and they're really clever observations. They had very little to play with, and they proved all these amazing results and very, very simple derivations. And it's possible to write down a self-contained account of all of that. And so in my lecture notes, I, among other things, in part 4, I actually worked these out. Okay, so thus, as I said, we went from Descartes in some sense to Laguerre for sure, to Fekete, Polya. Next, as I said, came Schonberg, who said that if A is Tn, then it has the variation diminishing property. So from here, I'm going to give you 2 directions to proceed. One is clearly if this suppose A is a totally non-negative matrix, then this property holds by Schonberg's theorem. Therefore, well, the point is S minus the sign changes in minus A times X exactly equal the sign changes in A times X. The sign changes don't, the number doesn't change. So, but clearly minus A doesn't even have 1 by 1 non-negative entries. It can have negative 1 by 1 entries if A has non-negative 1 by 1 entries, right? So what other matrices also satisfy the variation diminishing property? Because clearly it's not just the totally non-negative matrices. This characterization was carried out just 6 years after Schonberg by Theodor Motzkin in his PhD thesis on sign. This turns out to be the sign regular matrices, which is that for every size R, all the R by R determinants are non-negative, are of a particular sign, either positive or zero, non-negative or non-positive. So I wanted to spend one slide on Motzkin himself, just because he contributed to so many different areas of mathematics. It's remarkable. So first of all, his thesis itself had the Motzkin transposition theorem and the Fourier-Motzkin elimination algorithm, which are apparently seminal results in sort of linear program. It also contained this fundamental fact about in geometric combinatorics that a convex polyhedron is the Minkowski sum of a compact polytope, the finite part, and the polyhedral cone, the unbounded part. Yes, all of that was in his thesis. But beyond his PhD, he also studied what is now called the Motzkin number in combinatorics, about some number of chords, number of ways you can join marked points on a circle with chords. He gave the first example of a PID in commutative algebra, which is not a Euclidean domain. He gave not only that, he also provided some sort of ideal free proof of Hilbert's Nullstellensatz with some kind of quantitative bounds on something, degree bounds. I did not read that part fully. That appeared, I think, in the Schur Memoriam volume in Math Zeitschrift at some point. And he provided the first explicit polynomial in two variables that is non-negative or positive in 2 variables on the plane, but it is not a sum of squares of polynomial, because clearly sums of squares of polynomials are non-negative. This one is non-negative, but it is not a sum of squares. And this was an explicit example. Hilbert, I think, had proved that there exist such examples, but nobody had come up with one, and Motzkin did. This is, of course, famously Hilbert's 17th problem. Okay, so now, so that was one way to proceed, which is that, remember, Schonberg's theorem was if A is a totally non-negative matrix, then it has the variation diminishing property. The number of sign changes in the output vector is exceeded or is less than the sign changes in the input vector. The other, so one way was which matrices have this property? The answer is sign regular matrices. The other way to ask is what together with this property characterizes the totally non-negative matrices. So clearly alone that doesn't work, but can you find one more thing that works together with this variation diminishing property? The answer is yes. This is called the sign non-reversal property. And so for total positive matrices, let's say, if you take any x input vector non-zero, then there is a coordinate where, let's say I have a square matrix, right? Then it is totally positive if and only if, first of all, it has the variation diminishing property, and secondly, the sign non-reversal, which is that if you take any input non-zero vector, then there is a coordinate where the output vector has the same sign. The sign does not reverse. Okay, and again, you can talk about the non-strict sign non-reversal property, which is if x is non-zero, then there is a coordinate where the input is non-zero and the output has the same sign or the output is zero. So this is non-negative instead of positive. That's the non-strict sign non-reversal property. So it turns out that just like for sign regular matrices, this variation diminishing property is sufficient. It alone classifies the property altogether. This was known that these matrices are characterized by these two was known as early as Ganttmacher and Krein in 1950. But what we proved recently is you don't need the variation diminishing property at all. Total non-negative or total positive matrices are characterized just using the sign non-reversal property. And so that turns out to be a result that, so actually my postdoc, Prajesh Chaudhary here, he really led the work here. And there's a third co-author in IIT Kharagpur, Rajesh Kannan. But yeah, it was really Prajesh who came up with this result for sure. And even most of the rest of the paper, he really led the work. So given m and n integers bigger than k, bigger than 1, and any rectangular matrix, so fix the order of total positivity, fix the size of the matrix. The following are equivalent. The matrix is totally positive of order k, meaning all 1 by 1 matrices minors are positive, all 2 by 2 minors are positive, and so on till k by k. If and only if every square submatrix of size r less equals k has the sign non-reversal property. So this is very similar in flavor to the spectral property I told you, right? Every square submatrix, you don't just go for the eigenvalues of one matrix are positive. You don't just go for A has the sign non-reversal property. You go for the eigenvalues of every submatrix of that size or less. Similarly, here you go for the sign non-reversal property for every submatrix of that size or less. This is total positivity. Similarly, there's a total non-negative criterion, which is A is Tnk, if and only if every square submatrix of size R less equals k has a non-strict sign non-reversal property, and I don't even need to check it for every non-zero vector as I wanted. I need to check it for a single non-zero vector in R to the R. Single one. So that is even more striking, that you don't even need it for everyone. It's a finite set of conditions that classifies this one, whereas earlier sort of the variation diminishing property and the sign non-reversal were uncountable sets of conditions. But now we've come back to one condition for every square submatrix, which is really what the total non-negativity really was. Every minor, just one condition for one submatrix. Well, so is this one. So is property 2. And that is sort of another, so the same property for non-strict. Actually, Prajesh is completing work this week by himself in a single author paper. So this was his first paper on total positivity, and he's finishing a second, where he comes up with, he strengthens this condition to also use just one vector. So that's another remarkable result. And so these are very, very fundamental basic results. Now you don't really need a blackboard sort of to explain these. I can tell you that the input and output vector have one coordinate with the same sign. That's all you need. Okay, so this is sort of along the same lines as those results by Ganttmacher and Krein, and sort of, yeah. Okay, so that's so there are even more. So the moral sort of is even today, even in 2021, there are fundamental results about total positivity and total non-negativity that somehow remained uncovered until now. And the fact that this single vector could be used was sort of definitely uncovered. And even this non-strict sign non-reversal property, you can reduce the test sets even without a single vector, and partial results were known. But for total non-negativity, this was not known. For total positivity, some partial results were known. So this was completely new. Okay, so so now let me go back. So now to the thing before the history and this present history, if you will, this very recent history. I told you that there are these prototypical examples, the Gaussian and the one-sided exponential density function. I gave you two probability density functions, and I said that those two and their reflections about the origin for the Gaussian, that is itself, were the building blocks, were the atoms, and sort of you can build up every single Fourier frequency function from those. How? The answer again is on the slide, in the slide title, convolution. So first, let me tell you the convolution formula for the discrete case for the matrices. That is called the Cauchy-Binet formula. So given two matrices, A and B, of possibly rectangular sizes, they don't need to be equal. Their product is also has the same order of total non-negativity that both A and B do. So if A and B are both totally non-negative of a particular size or less, then so is their product. And that's literally the Cauchy-Binet formula. How do you prove that A times B is T and R? Here is the complete proof. AB, take I and J to be index sets of rows and columns from anywhere, size P less equals R. Then AB, I cross J, the principal, the I cross J square submatrix or minor of A times B. That means I just look at the rows of I indexed by A and the columns of B indexed by J. Sorry, A indexed by I. So I can forget all other rows of A and I can forget all other columns of B. And so this determinant is the same as the determinant of this matrix, which is I by I cross J, which is P by P. And the Cauchy-Binet formula says take all P tuples of index subsets from 1 through n and take A I cross A determinant, K, and take B K cross J determinant. Multiply the two, add them up across K, and you're done. That is the determinant here. But now because A and B are totally non-negative for size P, every one of these numbers is positive if they were TP and non-negative if they were Tn. So in particular, this is each summand is non-negative, so their sum is non-negative, and you're done. This turns out, so this is the complete proof for the discrete case that the product of Tn matrices is Tn, but this has a continuous version as well, that if you convolve two Fourier frequency functions, or even more generally two integrable Tn functions, then their convolution is also Tn, and that basically comes from taking sort of the continuous version of this determinant formula for finite sized matrices drawn from lambda 1 and lambda 2. Okay, so that's called the basic composition formula. It is due to Polya and Szego from their book on problems in analysis, and so on and so forth. And this simple fact that this convolution together with this idea will help us construct additional examples of PF functions from old ones. Right? So, okay, that is one recipe. So one tool is to use convolution. Fourier frequency functions are closed under convolution. Here are two other tools. If lambda is a PF function, then any sort of rescaling, change the origin, then that is a PF function. That's sort of clear. The matrices really don't change. The third one is equally simple. If you have a sequence of Fourier frequency functions converging pointwise, and let us say this function is integrable and non-degenerate, then this is also a Fourier frequency function. And so why? Because it just remains to check that it is totally non-negative, but that comes from here. The limit of totally non-negative functions is totally non-negative, right? Take any xj's, take any yk's, look at lambda n of xj minus yk, that submatrix clearly converges pointwise to lambda of xj minus yk. So the determinant converges and you're done. Okay, so these are the three tools I will use. These are the three bonds, right? The univalent bond, what I forget what is it called. Some covalent bond and electrovalent bond, right? So from my atoms, I'm building up molecules using these three different tools. One is convolution, one is shift the origin, and one is a change of origin and scale. Sorry, Schonberg used to call this change of origin and scale in his papers. And one is literally pointwise limits, nothing more than that. Okay, okay, so, and now, okay, I do need a fourth tool sort of thing to convolve. And this is called the bilateral Laplace transform. It's the integral over R, not over a smaller domain. The nice thing is it behaves very well with respect to convolution. Right? And this is usually defined for S either in the complex plane or usually on some maximal strip. You know, I don't care about the imaginary part, but the real part lies in some maximal strip of convergence and so on, rather than in C. Anyway, okay. So now what I consider is one-sided Fourier frequency functions, which are given by what I just defined for you earlier. The exponential density changed by origin, and well, for now it's just changed by scale. I will change it by origin on the next slide. Okay. So the Laplace transform of this Fourier frequency. So this is Fourier frequency because for A equal to 1 it was Fourier frequency, and now I use lambda of AX. So its Laplace transform is 1 over 1 plus AS. You can check this simple calculation. Now take countably, finitely or countably many, I could have taken bigger equals 0. That's also fine. That would take a finite convolution or I take countably many positive real numbers which are summable. Right? Then for each n, the partial product, the partial convolution product, phi a1 star phi an, is a one-sided Fourier frequency function. And because of this fact, its Laplace transform is just the finite product. Notice because the ages are summable, each of these is less than e raised to minus as in absolute value and so on. You can bound it this in absolute value by e raised to minus a mod s, right? And because the ages are summable, the limit of this is itself bounded above, but is absolutely convergent, e raised to minus s times summation mod aj, or well, aj actually, it's mod s times summation aj, right? Sorry. Right? So this is indeed a convergent, so these things are very well behaved. They converge to something whose the Laplace transforms converge to 1 over the infinite product. And now because that thing is itself convergent, I can take the Mellin transform, or let's say just the inverse Laplace transform, and I would get back a genuine honest to goodness function. Okay. So before I do that, so now I change the scale here. Now let me change the origin, shift the origin. So shifting the origin to delta gives me a one-sided PF function with Laplace transform of this kind. Okay. So again, this is convergent as n goes to infinity. And so because I said taking limits gives me a PF function, I get a Fourier frequency function with Laplace transform this thing. So you prove that it is integrable as well. You prove it's, of course, non-degenerate, and it is totally non-negative. So you use the inverse Laplace transform to go back to some function whose Laplace transform is this with the infinity here rather than n, but which is therefore a Fourier frequency function as well. The fact that it was a function is fine, but it's in fact a Fourier frequency function. And look at this function. Look at this Laplace transform of that function. Its reciprocal is this analytic function. In fact, entire function, e raised to delta s, delta bigger equals 0 times this product. But not only this is analytic, it turns out that this is a very special kind of analytic function. As I said, I'm telling you about things which are very old. This is also very old. This is more than 100 years old. Okay, I'll get to that in the next slide, or maybe at the bottom of the slide. But this is the theorem. So what I told you is, I told you that every analytic function of this kind can be obtained by just taking limits of Fourier frequency functions. In fact, these very, very simple atoms, right? These one-sided things shifted by origin and scale. I haven't used the Gaussian yet, and I won't use the Gaussian on the next slide. Remarkably, I showed that all of these guys are Laplace transforms of PF functions. Well, there are no others. That is a famous result of Schonberg, again in that same landmark paper. A function, let me say continuous, so that I don't have to worry about, inverse Laplace transform is recovered up to a set of measure 0 and so on. So let me just say continuous, and that will fix the set of measure 0 as well. So a function, let's say continuous on 0 infinity, which is a density function or a frequency function in Schonberg's language, is a one-sided Fourier frequency function which vanishes below the origin if and only if its Laplace transform is the reciprocal of this kind of a function, where the ages are non-negative real numbers and they are summable. And notice that 1 plus aj times s, this infinite product, is the limit of the partial products, these finite products. E raised to delta times s itself is also the limit of these polynomials, 1 plus delta s over n to the n. And this is really, maybe one teaches this in freshman calculus, but when I saw this paper, I sort of realized for the first time the significance of this limit that you teach calculus students. This entire thing is a polynomial with negative roots, right? If delta is 0 or a factors have all negative roots, and this is the limit of these polynomials. You can check it is uniform over compact sets, and there is a name for such classes of entire functions. These are called functions in the Laguerre-Polya class, right? And again, this is something that Laguerre was looking at in the 1880s and 1890s and so on. This is the Laguerre-Polya class and Schonberg result. So this was one-sided result, and now I will use the Gaussian version. So use the things on the positive semi-axis, use the reflections on the negative semi-axis. Those are again, all of these are Fourier frequency functions, and use the Gaussian. Fourier frequency function, a density function, if and only if the reciprocal of its Laplace transform is of this form, is the Gaussian times some delta. Delta can be a real number, the ages can be a real number, and you multiply by this infinite product of this form. Okay, and such that gamma plus summation aj square is less than infinity, and that's good enough to guarantee the convergence of these functions. These two classes of entire functions, the two-sided ones and the one-sided ones, were very well studied by Laguerre in the 1800s. Class are limit sets of real polynomials with real non-positive roots. These ones here. So that's why the Laplace transform at the origin equals 1. Right? Of course, you can also have the origin can be a root at some point. Right? So for that, I would need to have factors which are s power n. So, and anyway, modulo this extra factor of extra monomial, these are exactly the first class of Laguerre-Polya and the second class of Laguerre-Polya entire functions. And these were very, very classical objects studied, as I said, in the late 1800s by Laguerre and the early 1900s by Polya. I will tell you the references in the end of this talk. And they were studied also for connections to a very, very special entire function in 1859. And that is the hypothesis that I told you that will show up in this talk. So Polya initiated in 1927, after Polya and Schur even had done their work on multiplier sequences and so on. He initiated a study of functions gamma of lambda of t such that this thing, the Laplace transform, is only real zeros. Okay? Or yeah, maybe 1 over the Laplace transform is only real zeros. So real zeros and poles. So his work contains the following result. The Riemann psi function is in the Laguerre-Polya class if and only if the Riemann hypothesis is true. So this sort of, again, brought limelight and attention to this class of entire functions because people thought, if you can understand this Laguerre-Polya class very well, you can prove the Riemann hypothesis. And as I said, lots of work has been done by Schonberg and others and so on the Laguerre-Polya class. Unfortunately, the Riemann hypothesis remains unsolved 100 years later. Combined with Schonberg's result, this leads to even observations that were made last year by Gaussian on the archive. And somehow, as he notes, there is no reason why they should not have been made by Schonberg in his paper in 1951. But for 70 years, sort of nobody said it. And so now Gaussian decided to say it. And it's just that if you look at the small psi function, if this is a Polya frequency function, then again, the Riemann hypothesis is true. Why? Because, well, this is literally, coming from the fact that this is in the Laguerre-Polya class and it's a Laplace transform of this psi function. This is the inverse Laplace transform, as you can see. So this is just that Schonberg's result combined with Polya's 1927 result. No subtlety beyond that. But it's just that this observation was not written down or he couldn't find it. Anyway, so the Laguerre-Polya class is thus a distinguished one in several areas, from analysis, obviously, to this matrix theory, matrix analysis and Polya frequency functions, to number theory. And finally, then, the Laguerre-Polya, so I'll mention the thing that I mentioned Schur's name a bunch of times. I didn't tell you why. So from Laguerre-Polya functions to Polya-Schur multipliers, or I will write down the result going the other way, but of course, the Laguerre-Polya class came first. So this is related to Polya-Schur multipliers. The idea is very simple. Given the multiplier sequence, gamma 0, gamma 1, and so on, which is just a sequence of real numbers, look at it as an operator on the space of polynomials. What do I mean? I mean, given any polynomial, I multiply the constant term by gamma 0, the linear term by gamma 1, and so on. The nth term, degree n term by gamma n, and so on. And then the higher order monomials have 0, 0, 0 as coefficients, so it doesn't matter what I multiply them by. Right? So this is the operator on the space of polynomials. Which such operators preserve real rootedness? So we say that gamma is a multiplier sequence of the first kind if for all polynomials which are real rooted, gamma p has all real roots. So it preserves real rootedness on all spaces of polynomials. We say it is of the second kind. If you have polynomials with only the negative root polynomials, then it has preserving real roots. So there are fewer restrictions on the space of multiplier sequences than on the first kind. So the first kind will give you a smaller class of functions or sequences. The second kind will give you a bigger class of sequences because there are fewer restrictions. Okay. Theorem. So Laguerre and Polya classified the entire functions Laguerre-Polya class type 1, which is a smaller class, Laguerre-Polya class of entire functions type 2, which is a bigger class. Here we have multiplier sequences of the first kind, which is a smaller class, multiplier sequence of the second kind, type 2, which is a larger class. And Polya and Schur basically proved that if you look at the generating power series of this multiplier sequence, then it is of the first class if and only if the power series is of the Laguerre-Polya first class. It is of the second class if it's Laguerre-Polya of the second class. A sequence is a multiplier sequence of the first or second kind, if and only if gamma's generating function is in the first or second Laguerre-Polya. So it's a beautiful theorem, and it's actually not too bad to prove. And I actually work out the sketch of this this theorem. I worked the sketch out in my lecture notes again, as I said. So it's about 50, 60 pages. They are a little dense, and the margins are small. But yeah, all these things are. But this particular thing actually is worked out in one 10-page section or 14-page section, nothing more than that. And it starts fundamentally from, the Gauss-Lucas theorem, Malow's theorem, the Schur composition theorem, Laguerre's multiplier sequences, and all these classical results about real polynomials and where in the complex plane do their roots lie. It's just about root location. That was the hot topic, very, very fashionable at the turn of the century there. And so the Descartes' rule of science, how many positive roots or real roots are there in Descartes in a real polynomial? All these things were what people were studying at that time. And that led to Laguerre-Polya entire functions, limits of polynomials which are real-rooted. That led to Polya-Schur multipliers. And it's really beautiful. And it all fits inside these 10 pages, nothing more in my lecture notes. Anyway, so but none of those ideas are mine, of course. Everything is an homage, if you will, to people 100 years back at the very latest, even earlier than that. Okay. Anyways, now by Schonberg's results again, if this is in the first or second Laguerre-Polya class, then the reciprocal of that is a Laplace transform, if and only if, of a Polya frequency function. So again, Polya frequency, so the Laguerre-Polya class really connects to all these things. It connects to Polya-Schur multiplier sequences, it connects to Polya frequency functions, it connects to the Riemann hypothesis, and these are all 1920s, 1930s, or at most, this one was 1950s. Well, guess what? It also connects to results in 2010s or late 2000s. And this is the modern incarnation of the Laguerre-Polya-Schur program. Bourchier and Brandon in the late 2000s studied higher dimensional versions of this multiplier sequence that I told you on this slide. Okay, they studied, so multiplier sequences, what were they doing? They were sort of real root preserving, right? This is preserving real roots, or negative roots preserving to real roots. Well, these preserve, say, when can you say that a multiplier sequence preserves polynomials with roots in a disk going to the roots in the same disk, or roots in one region of the complex plane to roots in another region which are specified? And so Bourchier and Brandon really took this program forward to extrude a lot of such root preserving or root structured operator characterizations using very, very simple classical ideas and a mix of some modern ones as well. This enabled them, so they used something called real stability or hyperbolicity for multivariate polynomials. This enabled them to characterize linear operators preserving omega stability, as I said, for domains omega, whether left half plane or right or upper or domains or disks or lines or sectors. They proved conjectures of Charlie Johnson on matrix I forget the specific names. They proved many Lee-Yang type theorems. So they had a whole big program. And then with Tom Liggett, who recently passed away in UCLA, they developed the theory of negative dependence for strongly Rayleigh measures, and that allowed them to prove various conjectures in the literature, Liggett and Robert Pimentel and David Wagner. And this program of Polya-Schur and then Bourchier, Brandon, and so on, was taken forward, the stability and hyperbolicity, famously by Adam Marcus, Dan Spielman, and Nikhil Srivastava, this decade, or just the past decade now, to prove the Cadison-Singer conjecture, to prove the existence of bipartite Ramanujan graphs, and so on. So all of this really stems, though, from the turn of the 19th century to the 20th on root locations and polynomials and very, very simple questions, which are incredibly deep, which are profound implications, and all of this spectacular progress in the next 100 years, and even it's still ongoing. Okay, so these are the lecture notes that I mentioned. A half of that, which is not related to this talk, which is related to positivity preservers. I just submitted the draft on Friday to Cambridge Press, the final polished draft. So this will come out hopefully this year. The paper that I mentioned about the sign non-reversal property alone being sufficient to characterize TN or TP is joined with Prajesh Chaudhary, as I said, my postdoc here, and Rajesh Kannan in IIT Kharagpur. It's just accepted, I think, this month, last month now, it was just accepted. And now for the history. So Laguerre, this is the paper where Laguerre developed the Laguerre-Polya class, functions, the entire functions of genus 0 and 1. This is the thing where he developed extended Descartes' rule of signs, took it ahead. And this contains the seeds of variation diminishing property for the exponential, for the Polya frequency sequence, which are the coefficients of the exponential. Fekete and Polya proved, so Fekete said that Laguerre claimed this but didn't prove it. Fekete proved it here. Polya here developed the Laguerre-Polya class in a little more detail. Polya and Schur developed the theory of multipliers. And then Schonberg in 1930 proved that totally non-negative matrices have the Polya frequency property. And Schonberg in this paper, after two announcements in the 1940s in PNAS, he proved in this paper, he laid down the entire theory of Polya frequency functions. And in the 1950 paper, which was part 2, but published earlier, he proved that those functions have the variation diminishing property, and it's sort of an if and only if for functions, for kernels. Okay, so that's it. Sorry, I'm a little over. Yeah, I took about 1 hour. So thank you. Thank you for
that. Yeah, thank you for the insightful talk with such amazing results. Yeah, and now I will request anybody from the audience if they have any questions to ask.
And of course, you can email me if you know anything starts later on, or if you want more about the proofs or the references, I can let you know.
Yes, so you were talking about this Topliss forms and those things. So I don't know. This might be a very naive question, but this. So there are there characterization of variation diminishing property for Topliss matrices.
I think, as I said, so I think there's a paper by Schonberg which is on Polya frequency functions part 2. I believe says that those are the only ones or something like that. As the Polya frequency functions are the only ones. Let me just check it. I have my notes, lecture notes open. Let me check for 1 minute. Variation. If I have them there, I'll let you know. Variation diminishing property. So let's see. Okay, similar result of matrices for variation diminishing property of functions. And okay, Schonberg also proved this for polynomials. Okay, these are the one-sided results. No, I don't think I wrote them down. So, but I think, as I said, I think in this look at the paper in 1950 for this result, and that would be in let's see, that's in Acta Sci Math.
Okay,
it's there, but yeah, it's a paper in 1950, and it's a short paper. It's a 10-page paper basically. And that's where the title is on Polya frequency functions 2. Variation diminishing integral operators of the convolution type.
Okay.
My belief is he said that these are all the ones. Stop sharing this slide.
Okay, so if there are any more questions, then I would like to thank again Professor Khare. Please send us your slides so that we can upload it on the website.
Sure, absolutely. I'll do that.
Yeah.
Thanks. Yeah.
Okay. Then we'll end this webinar. And okay. Thank you, everybody. And thank you especially to you.